I would like to describe a field in which little has been done, but in which an enormous amount can be done. This field is not quite the same as the others in that it will tell us little of fundamental physics, but it will tell us much about the strange phenomena that occur just below our perception. In contrast to the natural philosophers of the past, the scientists of this field delve into the recesses of nature and show how she works in her hiding places. Their quest is to understand and create the imperceptible. After all, there is plenty of room at the bottom.
Hey everybody, welcome to the Materialism podcast, an exploration of the past, present, and future of material science and engineering. My name is Andrew Falkowski. I'm a PhD student at the University of Utah, and I'm joined by my trusty co-host, Dr. Taylor Sparks, of the same university, of the same department. And today, we are also joined by Kate Winning of Oxford Space Systems to help us dive into a really cool topic.
Yeah, it's ski season around here, so I'm waking up early and I'm headed up skiing. And one of the first things I do is I carefully choose my inner layers of clothing, right? I want the first one to be moisture wicking as you're climbing up the mountain. I don't want that sweat on me making me cold. I've got the outer layer, my shell layer, which is supposed to prevent, the wet snow from getting me wet from the outside. We sort of take for granted how much engineering has gone into these incredible materials that we put on our bodies every single day. And today, we're going to dive into that, right? We've done 14 or something episodes, and we've never talked about maybe the most used material of all, which is clothing and textiles. And Kate Winning is going to be our guest. She's going to walk us through this. She actually got her degree in textile design at the University of Arts London, and now she's working at Oxford Space Systems. You might be wondering, like, wait, hold a minute. Oxford Space Systems? Why did they hire a textile design expert? Well, you got to stay tuned. We're not going to tell you this episode. Today, in today's episode, we're going to talk about textiles from the sort of ground up. Kate, thanks for joining us. How are you doing?
I'm good, thank you. Thanks so much for having me on the podcast. It's really cool to actually be on here because I've mentioned before I've actually listened to the podcast ever since I started my journey into engineering for space, and you guys have been super helpful, teaching me lots of things that are super interesting and very helpful to get my head around and translate my textile knowledge into engineering.
Well, thanks for joining us. Maybe we get started with, before you can have textiles, which is like the woven product that we all wear or use or whatever the application is, you got to start with the precursors, which are the fibers. So, Andrew, we've got 4 main categories of fibers. Let's walk through them.
Yeah, so just at a high level, you have fibers that can come from animals. You can have them that come from plants. You can have so-called regenerated fibers. These are things where it has a natural origin, but by applying some chemical process, we can then turn that into a fiber that's slightly different chemically. Or we can have synthetic fibers, which are very common. But each of these is a little bit interesting because it varies, and because it's a natural product, these tend to exhibit a wide amount of variation. It's not like something that we can produce in a factory where we have consistent, repeatable results. There's going to be some natural variation, maybe even between the origins, but even within the origins themselves. So I think starting with the animal fibers and just doing a kind of a journey and a tour through all that these can contain will be a good start. These are going to be things like wool, which most people are familiar with. Its close relative, alpaca, cashmere, yak hair can also be used, or silk. There's many more beyond that, but those are, I think, the common ones that people encounter. Something I didn't know, and I discovered in preparing for this episode, was that cashmere actually comes from goats.
I didn't know that either, because it's like known as like a luxe, like very luxury item, and you don't think luxury when you think goats.
Yeah, it's only collected from the undercoat of a cashmere or pashmina goat. And for a long time, it was just like a practical, like everyday sort of warmth thing for shepherds, but it wasn't until the 18th century that it actually was discovered, and the shawl, the cashmere shawl, became like a high luxury status symbol.
That's cool. Something I enjoyed learning about in this episode is like animals evolve over time, right? If you've seen, like, there's been documentaries I remember watching on dogs where we literally turned dogs from wolves into the lovely house animals we have. Well, we've done the same thing with other species, including wool, right? So wool is actually a protein when it gets produced. So interestingly, it's actually more, from a chemical standpoint, it's a bit more similar to, say, silk than like a plant fiber, like a cotton. And And its structure that it creates is really what gives rise to its properties. It has these crimps and scales, which allows it to be bind together and easily felted. My daughter for Christmas last year got a felting kit. If you haven't seen these before, basically you can take wool and you stab it with little tiny needles and it will sort of gob together. And so this has that property that's possible to it due to its microstructure of having this sort of crimping and scaling possible there.
Interestingly, we actually domesticated sheep for milk and meat a long time before we actually started to domesticate them and genetically breed them or select for the wool. So it was like 11,000 to 9,000 BC is when we domesticated them or started to domesticate them for meat, but it wasn't until much later. And then once the sheep became and wool became more popular in Europe, you started to get more sophisticated breeding methods where they're trying to soften the wool because wool's pretty scratchy. And so you get the merino sheep in the Iberian Peninsula. And that was actually like a well-guarded breed. You couldn't, take that anywhere because it produced a really soft wool that was an economic advantage from a production standpoint.
And it's funny, even still today, like in the ski world, if you buy the really high-end base layers, they're merino wool, and they are expensive. You're looking at, significant money to buy just a base layer, but you get what you pay for, and they're really nice, high quality.
Another thing I didn't realize is that depending on the location on the sheep where you get the wool, it will have different properties. So the shoulders and the sides are a finer wool than things like the tail area or maybe the undercoat, which can be a little bit rougher. So where the wool comes from, I don't know if they actually sort it there in that way or if they just bundle it all up, but depending on where on the sheep you get it, it changes as well.
Oh, rad. This last fall, I got to take my son with me to China. I had some research, some work trip going on there. And while we were there, we went to Xi'an, which was sort of the departing point for the Silk Road. And we went to this giant theater production about the Silk Road. And it's phenomenal. Like, it's hard to overemphasize how impactful that was, not just for China and their economy, but for the world. Silk was really born out of there, and it goes back now thousands of years. What I think most people have heard this before is that silk comes from worms, right? The silkworm. It's kind of bizarre to think about it. But it's a very unique engineering material. First off, if you have a silk garment, which you probably do somewhere, you'll notice first thing about it is it is extremely smooth, extremely silky and sort of reflective of light. That's literally goes down to its structure. It's another protein, right? Fiber here. And it has this triangular prism-like structure that is responsible for refracting the light the way that it does, causing that shimmer. And it is also a crazy strong fiber, remarkably high strength. It's got pretty good moisture absorption, low thermal conductivity. It does get weaker when it gets wet, and it can be damaged. We always talk about like moths and things damaging silk garments if you don't watch out for them. But it's pretty awesome. They actually would harvest the cocoons of these little silkworms. They have to make true silk, like the best silk, they feed it something very specific even. They'll boil these down, and then they could extract the filaments from them, and those get spun into threads. So pretty wild. I always wonder, like, who was the first person to do this? What were they thinking? Like, I'm going to gather up these gobs of, like, worm cocoons and see what we can use it for, but, somehow it happened.
Something else that's kind of interesting is silk differs from a lot of the other fibers that come from the natural world in that it is a filament as opposed to a staple. That is, it's a continuous strand, a continuous polymer, as opposed to staples and what comes from wool and plants as well that we'll get into, are these shorter fibers that have to be adhered to one another by friction or some other agent. And the length of that staple can change the properties. They can have a different staple length. So as you might imagine, having a shorter length means you're going to have more fibers per square inch if you were going to form some sort of strand. And that actually makes for a much rougher fabric. So the longer the staple length, the
smoother the feel.
The smoother the feel. And that's why silk, being something that can be a continuous, feels so smooth and soft.
Yeah, that makes sense. Well, there's a gazillion other animal fibers, right? But let's move it along. Of our 4 categories, we started with animal, and now our next one is going to be plants, right? Plant-based. Every listener who's listening right now may well be wearing something cotton, right? Cotton, the fabric of our lives, it's become like this important, symbol. We use it all over the place. It also goes way, way, way back. In Peru, 6,000 BC, they were using this. It actually traveled around the globe, came to Europe through trade. Many now civilizations have independently found and domesticated it. It comes from a plant. It's actually the protective layer around the cotton plant seed. And some benefits about cotton is it's durable, whether it's wet or dry. Remember about silk where it loses its strength pretty significantly when it gets wet. Cotton is a durable, tough, fibrous material. And it also takes dyes well. It can change color, right? And so you can have all colors of the rainbow in your clothing. But it does have some downsides to it. For one, it shrinks, right? Right. It changes as a natural fiber. It does, when you introduce something non-natural, like introduce boiling water, where it doesn't experience that in nature, it's going to undergo a transformation in some cases. And it can also discolor after washing. So it doesn't, well, it dyes nicely. It doesn't always hold that. They do sort of, and you've seen a shirt 10 years later. It's not that vibrant shine that it was once before.
Yeah, and if you look up cotton, like it's all the fibers are all kind of bundled together. They're wavy and such. And when you're going to produce this into a larger yarn, which we'll get into, you have to stretch them. And so all of a sudden, but the fiber itself has a memory. And so all of a sudden you introduce heat and other things that can loosen things up, and it wants to go back to that crinkled up shape. And so that's kind of one of the driving forces of shrinkage.
I think it's probably an entropic thing, right? I think it's similar like a rubber band. A rubber band, when you stretch it, you're like aligning those fibers, which, there's an enthalpy and an entropy, but from an entropy standpoint, you're making it more ordered. And so it actually wants to go back to a more disordered state. I'm guessing it's something similar with these plant fibers that given the opportunity, they want to introduce a bit more conformational disorder.
Possibly. Another really old one is flax, or once it's in a woven form, it forms linen. Woven pieces of flax date back more than like 30,000 years. They found them in really old caves. And as early as 8000 BC, linen fabric was found in Swiss lake dwellings. It's been used in the mummification process in Egypt. Side note, I just rewatched the Mummy series with Brandon Fraser. The first one's actually...
It holds up, right?
It's kind of fun. It's definitely like a product of its time. But the second and third one would really fall off. The second one is worth a watch, though, for some of the goofy scenes, like... Some guy throws a snake at him and he catches the snake and then throws the snake back at the guy as a sort of self-defense measure. There's also a scene where the mummy from the first one, his scorpion king gets killed or something, and he like runs on scene and kneels and then shouts no. You have to wonder if there was, I don't know, if there were budgetary constraints or some sort of poor editing that happened there where they're like, okay, we just got to go with it.
We got one take. In listening to Get Ready for this episode, I was learning about linen a little bit. They did use it for mummification, and these things have held up. Like we joke about like the movie holding up over time, but like millennia later, some of these fabrics are still intact. How wild is that this plant fiber can last that long? Basically, it's like, as I understand it, flax, it's the stem, right? The stem, it's essentially the casing inside the stem that becomes the linen. Is that right?
No, it's actually it's more complicated than I would have thought. So you have the flax plant.
Yeah.
So it does have a stem, but it's actually, the fibers are in bundles within a particular layer of the stem.
Oh, it's not even the full stem. It's just
not
parts
the full
of it.
stem. So if you have this core region, you would then enter this more cellular region called the xylem. And then moving outwards, you get to something called the phloem. Yeah, Phloem. And there are these bundles of fibers, and those bundles and the fibers within are the flax fibers, the linen fibers.
I see. I'm reading here that it's the layer that's responsible for transporting nutrients. That makes sense, right? So these are going to be like tubular. They're going to be longer, right? So the staple, we talked about that, like the length of these things, they're going to tend to be a little bit longer, more continuous, which gives rise then to a nice textile to work with.
Yeah, and it's nice because it dries very quickly and it's very light, so it's perfect for really hot areas and environments. It tends to be a little bit rougher because these fibers are not circular and they're somewhat coarse. But they tend to soften up over time. I wonder if it's like a friction thing eventually just against your skin.
Yeah, we have some linen sheets and their whole thing is like, says right on the package, like better with each wash. And you kind of feel that it does sort of feel smoother with time.
Mm-hmm.
Okay, so that's our plant fibers. And again, just like there's a gazillion animals, I'm sure we could do many other plant fibers. Hemp, for example, right? Like I've seen people, I had a buddy in undergrad, maybe he's listening under this today, but he would wear a giant hemp suit and was so proud of it, and it looked ridiculous. But, there's other fibers out there for sure.
Sisal, abaca, bamboo fibers.
Yeah, bamboo can actually be pretty soft, right? I remember we had a baby, my first kid when he was still a baby, and they bought him a bamboo onesie, and I was like, oh, it's going to be terrible. No, it's so nice.
I have a bamboo shirt. It's held up.
It's
for
so
one, the dye is
nice.
held up, and it is really soft.
Yeah.
Apparently there's some environmental concerns there, though, because to get the fibers, it's also a similar, they call it a bast. So the flax fibers are called a bast, those bundles that exist kind of at the edge of the stem.
Okay.
Bamboo fibers are also a bast, but they're harder to get at because bamboo's hard. So they use this chemical process to extract them, and apparently it's somewhat environmentally harmful.
Yeah, here we're using a natural fiber thinking it's going to be sustainable, and yet because the chemicals necessary to get it out, it may not be. So that's actually a good segue to our next topic, which is regenerated filaments, right? And you said earlier that these are based in natural materials, but we have to do something to them to get them in the fiber format we want. So a good example is rayon, right? So if you start with wood pulp, you dissolve that, right? And now that it's dissolved, then if you do extrusion with an acid bath, then you end up creating a fiber. So yes, it's a natural material, but no, it's not totally natural. You really had to do some chemical engineering to this. You had to process it. This rayon is a good example because it was actually intended to be this silk alternative. It's soft, it's easy to dye. And there's others. And learning for this, I saw you put here in the notes, milk casein. You can make fibers out of milk, which sent me down this little rabbit hole. Back in the 30s and 40s, this was like all the rage. They were making fibers out of milk. How wild is that?
Yep, if you take skim milk and then similar process, you extrude it into an acid, it'll coagulate into a fiber, and you can draw that out.
So rayon is the big one here. Acetate, there's another one. But really that's now kind of bridging. These are looking less like real natural materials and more like something synthetic, which bridges to our last category, which is full-on synthetic fibers. And just like you are probably wearing something cotton today, you're also probably wearing something synthetic nowadays, especially because you can blend these things together, right? So synthetic materials, the things that come to mind are polyesters, spandex, aramids, polyurethane, PVC, believe it or not, right? PVC, right? All these things, you can turn them into fibers that you can wear. Polyester is super popular, right? This came around in the 40s. British chemists did it. It's the most produced fiber nowadays, polyesters and everything. And there's good reason for that, right? It's strong, it's wrinkle resistant, it's quick drying, inexpensive. Because it is based out of petroleum, typically how we make it, it's easier to control it. There's not this sort of variation that comes from natural processes. Anyways, you take basically purified terephthalic acid, PTA, and you take ethylene glycol. These get combined to form the polymer, which is polyester. It makes a polyethylene terephthalate, PET. The same stuff, by the way, if you had like an old Nalgene bottle, like that really hard, rigid plastic, that's the same base material. It's just whether or not you made a monolith of it or whether you spin it into these thin fibers. But it's that same strong material, so no wonder it's going to make a really great fabric.
Yeah, and from an industrial standpoint, I mean, quality control matters quite a bit. So with a natural fiber, we've gotten a lot better at processing them and doing selective breeding to produce more consistent results, but you could have variation from lot to lot. Here, you're probably seeing some variation, but probably quite a bit less, allowing you to produce the same textile pretty continuously and consistently.
And there's other synthetic materials, like lots of them, obviously. One that we've got listed here is aramids, right? Just because they're really interesting. Aramids, if you're familiar with chemistry, this is the one that has the benzene ring in the backbone of it. So the types of polymers that you might have heard of are things like Kevlar, right, or nylon. These things tend to be extremely strong, that aromatic ring does not rotate very easily, which makes them add some rigidity to the structure. So unsurprisingly, these aramid fibers are associated with strength, right? These are high strength. They can be extremely strong in tension while keeping, obviously, the lightweight benefit of the fact that they're fibers. And a lot of these are resistant to high temperatures. These are strong chemical bonds in them. So if you're making bulletproof vests and things like that, it's often going to be made of these types of synthetic fibers.
They're very stiff, though. They're not very comfortable to wear.
No. And then obviously there's a gazillion others that we could come up with. When I was a intern doing my very first material science internship, I was working at Ceramatech, and we were making some insulation materials, and we started with ceramic fibers. And I remember asking, like, wait, what? And they're like, that's alumina. I was like, alumina? Like you can make dishes out of it? Like, oh yeah, but it's in fiber form and you could wrap it. It was like clothing. And we would obviously impregnate it with like a matrix after we got it wrapped. So it ended up being a composite. But that was my first time seeing a ceramic in fiber form, which I thought was pretty cool.
Yeah, I mean, isn't insulation, it's a molten rock that is extruded into kind of a fibrous mass. They can also do this with metal fibers, which we'll get into a little bit later, where you can extrude very thin wires. I mean, everyone's seen copper wires. That's a fiber.
Yeah. Okay, so those are our 4 fiber types. A couple, we're going to have Kate really offer her expertise here in a moment, because when you go from fiber to textile, there's a whole nother layer of magic that I knew nothing about before this episode. But just a couple key material science concepts while we're talking about the materials before we get into the structures we make out of them. You've heard of these things if you've taken a material science course before, but there's 3 main things we want to talk about. There's crystallinity and amorphous, there's glassy transition temperature, and then there's like hygroscopy, like does it want or not want water? So let's start with crystallinity. In polymers, one of the cool design components of polymers is that it doesn't have to be either amorphous or crystalline, but it can have some mixture, right? You can have regions that are crystalline, and then you can have regions between those that are very much not crystalline, right? That ability to have this as a tunable parameter is really important for fibers, right? For one thing, in the crystalline region, you're going to have more anisotropic materials properties, right? Along the chains, for example, you're going to get a very different strength than outside of them. But in the amorphous region, it's going to behave a little more isotropically, right? Take, for example, our high crystallinity polymers, like the aramids. We said these things don't like to flex, right? They're going to tend to be longer and straight, the Kevlar, right? That's going to give you higher strength along these directions. But then if you look at other polymers that tend to be more amorphics, take spandex, right? It's going to allow for greater elasticity as these chains are able to slide past one another, eventually catching. So it's an awesome design parameter that we have available to us.
Another thing you'll see is glass transition temperature. This actually affects your ability to, in some sense, post-process your clothing. For example, ironing. If you have cotton clothes, they wrinkle after they come out of the wash or even through everyday wear. And if you want to spiff them up, make sure you show up at the office looking nice and sharp, you're going to need to iron them. And so by applying that heat, what you're doing is actually raising it above its glass transition temperature, from which it's going to go from a more brittle state to something more rubbery, capable of flowing. And that's going to take those fibers and those wrinkles that are kind of kinks and bends and allow them to be smoothed out. The application of moisture also helps sort of lubricate the fibers such that they can slide past one another a little bit easier and probably soften them a little bit as well. This is also why the glass transition temperature is also why some synthetics feel really stiff and crunchy in the cold weather, because normally they're in that rubbery state. And then if you take them into cold weather, they crinkle up.
Then that last material property is hygroscopy, or how it interacts with moisture. Does it wick moisture? Does it absorb moisture? Again, going back to my ski base layer example, once upon a time when I didn't have like nice base layers, I would just use cotton, right? And as they say, cotton kills, right? In camping, if you're out in cold, wet environments and you're wearing cotton, it's really bad for a couple reasons. First off, when cotton absorbs moisture, that moisture goes into the air pockets, which were responsible for providing insulation. So you lose your ability to prevent heat transfer, which means your body's heat easily gets transferred to the environment around you. It also is in contact with the skin, and so you get the evaporative cooling problem where your body, as the water turns into a vapor, it's absorbing energy that has to come from somewhere. It's coming from your body. So cotton kills. Now compare that to something like wool. I was surprised in getting ready for this episode. I saw that Andrew had the number here that wool can absorb 30% of its weight in water without feeling wet. That surprised me, because I was thinking wool is like this really high-end material for base layers, and yet here you're telling me it's absorbing. But when we dug into it, we learned that while it absorbs the water, it doesn't lose its insulating properties, first off, because of we described earlier, the fact that it has these crimped sort of microstructure. It can retain pockets for reduced thermal conductivity. And the other thing is that the absorption process itself is actually slightly exothermic. It actually gives off a little bit of heat, even as it absorbs water, which is pretty rad. And Andrew also pointed out that, wool as received is different than after you've washed it, because apparently it has an oil layer, right? A lanolin layer, which changes its hydrophobic or hydrophilic properties. So wool as received is going to be different than once you've washed that clothing.
Yeah, I'm not sure how easy it is to wash that off, and how how much it remains in a lot of the wool clothing that we purchase. I guess it probably depends on how the wool is being used, because you can have, like, your big cable knit kind of honky chonky
Yeah.
wool sweater, versus you can have t-shirts made of wool, which are, I don't know if I'd wear a wool t-shirt, but I assume those are processed quite a bit more heavily,
Yeah.
compared to one of those big sweaters.
All right, Kate, you've been a good sport. You've let us sort of set the stage for you. We've talked about the fibers, a little bit of the material science. We want you to help explain how you go from the materials now to products and what engineering and science is involved in that. Maybe let's start with yarns, right? You said that you start with these things on the spool. That's the yarn. Tell us about those.
So I guess I'd start from, when I'll use weaving it as an example, since that's my kind of speciality. If I'm going to create a woven fabric, I want to think about what yarn am I going to use. So that would be a yarn that's made from a fiber. Now you can make yarns from different fibers, but I'll just stick to single fiber yarns. So if I'm designing for winter, for example, I'll be looking at more wool yarns and ones like that. And then for summer, you'd be using cotton or linen. But then it starts to get a bit complicated because you want to also have, you think about the thickness of your fabric, so the drape of it. And that's where you start changing the setup of your loom. So the loom is what you weave on. And with that, yeah, you need to really think carefully about how you set it up, because if you set it wrong, you're going to have a very either tightly woven fabric or super loose, and depends what you're designing for.
And to go from the fiber state to a yarn is not just a matter of like collecting the fibers and then just like spinning them together. Some of these require, especially for coming from like the plants and the animals, require a good deal of pre-processing as well. Like for wool, like you have to clean the wool because sheep are kind of dirty animals and the wool hangs off them. They roll around in the mud and seeds and insects and things. They call this skirting and scouring. And then also wool is usually just kind of like a chaotic jumble. So they have to card and comb and straighten out these fibers. Then usually they're drawing this to thin them down, like you said. We don't want to just start with a maybe too thick of a fiber or maybe too thin. We want it to get it to a specific size. And then usually twisting these together, we mentioned this idea of like staple versus filament.
Yeah, well, if it's not super long, you've got to attach them to each other, right?
Yeah, so the spinning, basically, it's taking those scales that are on the wool fibers and it can cause them to hook together, and that friction kind of keeps them together.
Yeah, I would also say as well, even once you've got your yarn, and then you've made your fabric, you still have to wash and process that. So at university, it was a real experience realizing that you then needed to take all of your fabric home and wash it because the drape and everything changed, and ironing it. And something you were mentioning earlier, I was thinking about wool again, and with the when heat is applied to it, I had a interesting experience with with what's called a warp. So the all of the yarn together, and that's what you put on the loom to weave with. I had made a warp from dyed yarn that was wool, and I didn't realize that it had made it very brittle in the heating process. So when I went to tension it onto the loom, I actually ended up ripping a clump of wool with my hands because it had suddenly become extremely brittle. And that's where everybody in the class learned how annoying it is to weave with wool, because it snaps a lot. So I then decided I like to work with much stronger yarns.
Is that why hand knitting is so popular? It's probably a lot less tension on it. Or
I imagine.
I guess a lot of things are still are manufactured at this point. So it probably just comes with the territory of using wool.
So I guess that this is where we could start going into all the looms and weaving and knitting machines. So knitting, generally is when you refer to the hand knitting. So that's all controlled through, by your hands, and once you become more advanced with knitting, you get really good at controlling the loop, like the loops that are put onto the needles. When you first start knitting, you'll notice that all your loops are lots of different sizes because you're not very good at controlling the tension of it. But as you get better, obviously the loops are, much more consistent. But weaving's completely different. Like you can have a little frame to weave with at the most basic level, but you still need to control how much you're pulling the yarn through the frame, because you'll end up getting really uneven sides of your fabric. So it is actually you need a lot of practice. I mean, you can do basic knitting and weaving, but if you want a nice consistent fabric that has a good drape, you might want to practice a bit.
Yeah, and I imagine the tightness will probably affect the feel of the fabric as well.
Oh, for sure.
I don't know if this is true, but we had a family friend from South Africa, and he was boasting that he had this shirt that was woven so tightly that the mosquito's needle mouth thing could not puncture through it.
Proboscis not allowed.
I don't know if that's true or even possible, but that would probably take quite a bit more fabric or quite a bit more yarn in order to actually get something that tight. And I'm sure the properties of that yarn matter too. Something that was kind of interesting is you mentioned single versus multi-material yarns, is that you can take a yarn if it's smaller, and then you can do, I think it's called cross-plying or multiply, in which you join different yarns together. So that can be multiple of the same yarn in terms of like a bunch of different wool just to make a thicker fiber, or it can be different materials. So when you see like a blend in your clothing, usually that's referring to the yarn that's being made could have a little bit of spandex in it, for example.
Interesting.
Or a little bit of polyester to either reduce cost, improve the feel.
Combining different materials, it sounds tricky. I like to make things like costumes, and a couple years ago I made this Star Wars sweater, and it was using e-textiles, like wearable textiles, right? Wearable electronics, excuse me. So I actually took a sweater, which was probably some cotton poly blend, and then I was going to sew with a stainless steel yarn that I bought online. I was going to sew the lines of conduction, right? So that from the little Arduino lily pad thing I had on the heart, it looked like a Death Star. It was pretty rad, right? From there, I would sew it out to a little LED, and that would provide the power for it. The circuit was the actual sewed path, which is awesome until you start to make a complex circuit where, because these are like exposed wires without an insulating shell over them, if they had to cross over each other, they would short out. So this is all happening on the back side of the shirt. I was like putting felt layers down with like hot glue to insulate it. It turned into an absolute monstrosity, like a total disaster. And my mom, who's an amazing sewer, she's an awesome seamstress, she was loading this stainless steel bobbins into her sewing machine, and it kept on ripping. She's like, what is this? This is the worst thing I've ever sewed with. So in the end, even though it's technically possible to have these electronic fabrics, right, that you turn into a device, we bailed on it, right? I stitched like so much. I'll put a link in the show description. Check it out. We've got a fun YouTube where I put this together. But in the end, I ended up taking fiber optic cable from like Cat5 cable that you delivered like internet with, because those are super thin but insulated copper wires. And I just passed those on the inside of the sweater because it was really hard to make the sewed fabric work as a electronic pathway.
Was this before we started the podcast? Because I remember going to the department sweater contest and you showed up in this and you said it was really hot.
Oh, it was awful. And it was probably going to catch fire, right? It was like an absolute hazard. I think it was like just before we started the podcast. Anyways, check it out in the show notes. But sort of coming back to weaving, it made me think of this because you said controlling the stiffness and how tight these things come together is hard enough with a single fabric. And it just made me think, okay, as soon as you start to introduce blends where you've got very different materials properties, different elastic response, different ductility, it's going to be even harder.
Yeah, I mean, it's funny when I first started weaving because, in the shops you just see regular kind of simple patterns and a normal drape of a fabric. But, if you really go crazy with it, you can make such a weird, thick fabric that doesn't really make sense. So it's when you've first taught about weaving, you kind of, you're just sent out to like pick whatever yarns you want and figure out how the loom works. And, you should see the first weaves I made. They're a complete mix of materials. Like there's no thought of
Oh yeah.
I've got a wool right next to the like a really thick synthetic yarn. It's completely impractical, but it looks cool. And then as you start getting used to what you're making, you start thinking more about, okay, I need to just use logical yarns for this, and then you get used to working with the yarns, and you get used to how to set up the machine to make a fabric with the correct drape, not some weird bunch stuff in one area and really loose in another area. So it's quite, there's a lot to know about it. You can do very basic weaving, but if you want to, design something for a specific brief, you need to know what you're doing with the setup. And it is, even to this day, I still struggle with, there's something called like ends per inch with weaving. So in an inch, you wouldn't want too few or too many yarns. So that's what defines the drape at the end, pretty much.
Is this what's meant by, I go into these stores that have like bedding or whatever, and they're like, oh, this is 300 thread count and this is 1,000 thread count, and is that what's determining the difference here? Okay,
I think so. So that's where you'd get a thicker or heavier drape or a lighter drape.
Okay, I don't think you mentioned this already, but can you explain warp and weft when it comes to weaving? As I understand it, like part of the fibers have to stay stationary, and then the other fabric yarns are woven around them. Can you explain this?
Yeah, I think that would be a good explanation, because when you start talking about looms and weaving, it's probably really confusing. So I think the best way to describe a warp is like the vertical lines in a grid, and then the weft is the horizontal lines in a grid. And if you were to follow a grid pattern, the most basic fabric you would get is a plain weave fabric. So it's literally just interlacing up and down yarns, basically.
Like a trellis, like on the top of a pie or something.
Yeah, exactly,
Okay.
yeah.
But you can do more complex ones. I'm teaching a sports gear class where we're talking about composites right now. And I was just introducing the idea that, hey, you can weave these carbon fibers into all sorts of different shapes. You can do like a 090 ply, and then the next layer up could be like a negative 45, positive 45 or whatever. Can you, I know we do have the same capability of introducing different degrees and biases in our weaves. How do you, like, as you're a textile design person, right? There's a bunch of these that were invented long ago and you just sort of select from them? Or are you actively like designing new waves and directions to weave these things together?
Yeah, so you can get really complicated with your warps. I think it would be difficult to explain it verbally without any diagrams, but I suppose if I tell you about what's called an arm loom, so it's a much bigger loom, and you, instead of kind of lifting up the yarns by hand, it's all like automated. So you can program the loom basically to lift up different bits of your warp, let's say, and then it lifts them up in a different, more spaced out, because on a table loom you can only lift up like 8 yarns at a time, whereas on an arm loom you can lift up to 24 in different sections. So that's already probably a bit confusing, but basically you can draw on the more advanced machines, you can draw like quite intricate patterns onto the loom, and just by pressing the pedals, then it lifts it up in a more complicated order, and then you can program, really like one part of the fabric can have a really intricate pattern, and then another like right next to it will be doing something else, and then you can kind of puzzle that together to make an overall big pattern.
Oh geez.
It's
fast.
really
Yeah.
it is really confusing.
I've seen that on some shirts where it just has a totally different texture in different parts of the textile. The other example is that I saw when I was doing research is satin, for example. It's not a different material, it's actually a different weave. And so if you think of like your plain weave as going like alternating, like I think you had mentioned earlier, or when we were talking in preparation for this episode, like a plain weave is like a checkerboard in terms of alternating over under of the weft over the warp. Satin has larger areas of it being over versus under. And so having more over means there's more smooth fabric. You don't have as many interfaces that your skin's in contact with, and that's what kind of makes it shinier and a little bit softer. Is that right?
Yeah, so there's also the satin and sateen weave. So one satin, I can't remember which one's which, but satin shows more of the warp, whereas sateen shows more of the weft.
Oh.
And is it just a matter of like flipping it from one side to the other? Like on the satin is like the outside and sateen is the inside. Is that as simple as it is, or?
Yeah, if you just use so if you had like a jacquard pattern, which is in the most basic way to explain it is just when you have a pattern towel, you sometimes you can see on the other side like the reverse pattern or with a jumper as well, like it's mirrored the other color.
Yeah.
So that's one example of that. And yeah, you can use satin and sateen weave to kind of change that a bit, I think. But you can only do that on a jacquard loom, really. So the kind of industrial version of the weaving machine. So you have your table loom, which is your most basic, then the arm loom, which is what I was trying to explain with the slightly more complicated warp setup. And then you can have like industrial looms where each individual warp thread can be lifted up, because in the other examples it lifts up big sections of it. But yeah, the industrial ones lift up singular yarns.
Wow.
And then, like I said, you can have more of the warp showing or more of the weft showing. And then if you do a jacquard pattern, it's just mirrored on both sides.
So you mentioned the jacquard pattern. In getting ready for this episode, I learned about the jacquard loom. And I'm curious if ChatGPT was just making this up, but it claims that this invention, which shows up in the early 1800s, way before computing, was nevertheless a loom that actually used punch cards to control the weave pattern. So as I was reading that, I'm thinking like, oh, that's like early Fortran, where like the code was literally encoded on these cards that you pass through it. Was it making this up, or is that for real?
Yeah, we did have a big. I never got to use it, but there was a big loom in our weave studio that had the punch cards. So yeah, you would. So how I was saying, you'd digitally just draw a pattern on, and it's so easy, and then the loom just does it for you by moving your feet.
That's so cool.
Way back then, you would have had to punch the pattern in. I never actually learned how to do that, but like.
But what a cool precursor to like modern computing! I think that's awesome that came out of the textile industry.
Yeah, for sure.
Yeah, looking at some of the more advanced kind of technical textiles, and how engineers are approaching them, they're using kind of like a digital version of a punch card, where weaving patterns can be presented as these binary grids where you can, different colors indicate the warp versus the weft. And you can actually have these algorithmic tools. There's software, there's something called like TextGen or Weaver or Weavecraft. These are tools that allow you to weave patterns, and you can export them into like finite element analysis and actually get like mechanical properties. So for your cotton shirt, this probably is not happening. But for, a bulletproof vest where you're trying to understand how different weave patterns are going to respond to a projectile, something like this might be pretty useful.
I learned too also, you can actually make 3D weaving. Is that right, Kate?
Yeah, I think so. And I went to a textile conference and I saw some crazy looms where there were warps kind of coming in from all sides of the machine.
Yeah, if you just go to Google Image, like you can see a picture of a shoe. The entire thing was a 3D weaving to produce this shoe. So I'm wondering if that's like on the forefront of things to be further developed, or if that's what's the state of that?
I think it's actually being used in GE's LEAP engine for the external carbon fiber turbine blades. So the way this works, from my understanding, just from like a very brief Googling, is if a weave is like a 2D plane, the 3D weave now has the machine has the ability to now do a kind of a Z-axis to actually bind multiple 2D layers together. And I think for a composite material to create a fully kind of monolithic form of the pre-impregnated carbon fibers in the shape of a turbine blade, they're able to do that with one of these 3D looms. And then they apply some sort of matrix material to give it form.
It's cool.
So I think the next thing we might want to dive into is knitting. Kate, do you want to? We talked a little bit about knitting, but maybe if you want to give us a little bit of introduction of the idea behind knitting, where it shows up, which is more often than I thought, and maybe the difference between weft and warp knitting?
So knitting is just basically weaving's sister. It's instead of a linear grid, it's more of a loopy grid, and it's made in its most basic form. You knit with one yarn, whereas weaving is with multiple yarns. And you can do it with the needles. That's the most classic example. And then there's lots of other machinery that you can use. Again, advancing. There's the home weaving knitting machines that you can use, and then there's the industrial knitting machines, and then warp and what's the other one?
I think weft knitting is usually the one that you see most common. It's the one with the needles where you're going kind of across and building up these materials layer by layer. But like you said, it's a single yarn. But I think warp is different.
Yeah, warp is I haven't worked with warp knitting. Weft knitting is what I've worked with. So that's imagine lots of if you've ever done crocheting, it's like it's a needle with a hook at the end. So industrial knitting machines kind of have all these needles with hooks at the ends of them, and depending on the gauge of the machine, you can have really fine gauge, so you get a really fine knit. And that's what I work with. So it's just all of the needles kind of go up in a pattern, and the latches move in a different way to create a different loop, which then creates a different knit pattern.
Gotcha. I think for warp knitting, from my reading, rather than a single thread, it has tons of different threads, and then it basically builds up a pattern kind of upwards by interweaving those together.
So the horizontal one's stationary now, and the vertical ones are changing?
No, think about them almost twisting together as you build upwards.
Okay.
So forming, rather than a sort of building row by row, you're building column-wise and connecting them. But because it's many yarns, there's the potential for it to be a little bit more robust. If you're using a very basic knitting pattern, I think there's this common thread, especially historically, of like if you pull one thread, you can pull apart the entire structure because it is just one continuous thread. So, the weakest link sort of theory applies here. Although I guess there are much more sophisticated weft patterns that can help avoid this and make it much more robust to things like this. But with a warp, you have so many different threads that one can fail without necessarily compromising the whole structure.
Yeah, you can definitely make more advanced structures that don't, like, they're anti-ladder structures. So yeah, with regular, if you knit normally with needles and you snap one yarn, that was just the one yarn, so it's a compromised fabric. Whereas I think I told you about there was a tights company that they somehow managed to make these indestructible tights. They must have used like an anti-ladder structure and then a really strong yarn, because they literally, in their promo, they have a cheese grater in the tights and they're just pulling at it and nothing's happening to it.
Oh, that's right.
So yeah, you can get really strong knit structures. So it's not always true that they'll just fall apart if you pull one strand.
So we have done, as much as we've talked, we've barely scratched the surface on the different types of yarns and weaves, but at least we've kind of set the stage for the engineering of these different materials. So now the next question is, what do you do with them? What are these applications? And we definitely plan on having a future episode where we go into a lot greater depth, but just briefly, let's cover a few of the things that you can cover. Obviously, clothing. We've mentioned that over and over today. Clothing is definitely one application, very important one. Carbon fiber composites and preforms is another one, right? So in my sporting good class, we're talking about making skis and all these other things. But those are, if they're made of carbon fibers, then that is also a byproduct of our ability to weave and make fibers. And then you can get into medical applications. Tell us a bit about those, Andrew.
Yeah, I mean, so if you think about grafts or other or tissue, it's flexible but somewhat strong. So if you were going to try to patch an organ, for example, you want something that's going to be strong, potentially provide a lattice on which cells can grow or be stabilized, but also have flexibility because it's got to squish and push against other things. And so textiles end up being a really great solution for this. You can get like vascular grafts, tissue engineering scaffolds, stents for the heart is actually a really interesting application where they can start out very small and then through the pulling on a certain direction or such, they can expand outward. So you can allow it for, a nice small package in order to actually perform the surgery, but allow it to expand in its application.
My buddy just had a hernia surgery like 2 weeks ago, where literally like a bit of your guts are like poking through a hole where they shouldn't be poking through is a hernia. And to fix it, I learned they actually put a mesh. They put a little surgical mesh there to hold it in place. And if you don't take it easy and let this thing heal on its own like it's properly supposed to, it can actually push through and break that mesh. And he might actually have that happening right now. So cool application of a biological surgical mesh material that either stays permanently or dissolves away. I guess there's different varieties, but
there's also compression bandages and other sort of textiles for healing in a certain way that puts appropriate pressure on it. But it extends much further beyond this. The tendons that stabilize ocean structures are these braided fiber constructions. So if you see those wind turbines that are out in the ocean or oil rigs, they're not like cemented into the sea floor. They're actually being held in place by cables.
Oh, interesting. I didn't know that.
Ballistics protection, which if you go back to one of our earlier episodes, we talked quite a bit about how there are very complicated weaves that are being developed to make sure that energy is traveling down our fibers and using the fibers to the best of their ability while also maintaining something comfortable. And then something that Kate can tell us a little bit about as a teaser for an upcoming episode are the idea of using textiles in space applications for deployable structures. Kate, can you tell us a little bit about that?
Yes, so I suppose, without spoiling it too much, the company I work for, they use technical textiles as part of their deployable antennas for satellites in space. And the reason why they need to be deployable is so they can fit in the rocket, which is cool. So we work a lot with technical textiles, and then it's the challenge of integrating them to structures.
So if you thought my Star Wars sweater was complicated with little metal patterns to conduct LEDs, buckle up. We're going to make antennas out of these things. Very complex, very, very cool.
And one last application, because even civil engineers can't get away from textiles. Under railroads and roads in general, there's large woven mats that are buried down there to prevent lateral soil movement. So as the soil tries to spread under the weight of a vehicle, it creates tension in the textile, which locks the soil in place. Didn't know this.
Very cool.
But textiles are everywhere.
They'll put them on to prevent road erosion, like on steep cliffs. They'll put them there as well to sort of encourage regrowth and prevent erosion as well.
Okay, well, this was a really exciting episode. We started this, and the more I was reading, the more fascinated I got, and the more I also realized how difficult it would be to contain this topic within a single episode. Textiles are a really cool hierarchical material. You start out with the fibers and where they come from. How do you process them to get the best of their properties? But that's not the end of the story. You then get into the yarns and how you're going to combine them together. So you're already forming a composite even at that level. And then you build up to these different weaves and knits and how many interesting and different applications they come across as well. We're really thrilled to have Kate on here to help break down some of the more complicated weaving and knitting terminology. Anything else you'd like to add before we jump off?
Thank you so much for having me. It was really interesting to talk to you guys. I hope my explanations of looms and everything didn't blow anyone's mind.
We appreciate it, Kate. I look forward to having you on again and learning about textiles in space.
Thank you.
Okay, we'll see you guys next time.
Bye.
See you.
Hey, we want to remind our listeners that today's episode is sponsored by Momentum Transfer. I've said it before, but having access to synchrotron data for powder X-ray diffraction is an absolute game changer. The resolution and intensity allows you to access information about your materials that are just not accessible with lab X-ray. And now with this company, you can get access to that synchrotron data without time-consuming proposals, waiting for them to get approved, sending somebody to go actually do the measurements. It's an absolute game changer. I love their business model. I hope you'll take advantage of it. And they've made it possible. In fact, if you go to momentum-transfer.com and you sign up, then you'll be able to get total scattering and PXRD measurements for 5 samples for free. You just can't beat that. So check them out.
And then lastly, thanks to the people that make the music for the show. Thanks for the listeners who reach out and suggest episodes like today's on Phase Field. You can get a hold of us. We are materialism.podcast@gmail.com or the @materialism.podcast on Instagram or pretty much wherever else. We would love to hear what you want to hear next. So drop a comment, whether this is on Spotify or on YouTube or wherever you're listening to this. Leave a comment. I try and get to all of those. Send us a message on Instagram. We try and respond to everything because we appreciate our listeners. We love that you're out there. And with that said, we will wrap it up and we'll see you in the new year. See you, everybody.
The inventors of fire, electricity, magnetism, iron, lead, glass, silk, cotton, the makers of tools, the captors of lightning, the architect, the engineer, the musician, are all beneficiaries of the materials of this world and are bound only by their imaginations in manipulating those materials.